We next have exercises on modular arithmetic. So in this one, we have to perform these calculations, but in this system, in the set of all congruence classes modulo 7. The modulus is 7. And so here, for example, 2 is not the ordinary integer 2, but 2 is the congruence class modulus 7 that contains the ordinary integer 2, which by the definition of that class is the set of all integers of this form 7m plus 2, where m is any integer. So actually this 2 is not ordinary integer 2, but it's a subset of the set of integers. However, we write this thing as 2 for the sake of simplicity, that's all. The interpretation should be like this. And that's why the operations we see here, this minus, for example, these are not ordinary operations that we have in the system of integers, but they are the two operations involved in this case are addition modulo 7 and multiplication modulo 7. So let's now see the solution. This ordinarily, if you calculate this, it becomes minus 10, but minus 10 is congruent to 4 mod 7. So the congruence class containing minus 10 and the congruence class containing 4 modulo 7 are the same thing. So the answer is this, but which is also this in this sense. Okay, so the extra requirement here is also being satisfied. The answer should be a non-negative integer no larger than 6. It should be less than or equal to 6 and greater than or equal to 0. Then for the second one, we do it in two parts. We first see what 4 times 5 is. Note that four times 5 is ordinarily 20. That means we are considering the congruence class containing 20, which is also equal to the congruence class containing minus 1, because 20 is congruent to minus 1 mod 7. 20 minus minus 1 is divisible by 7, which is 21. So using the operation multiplication mod 7, we get this. So here the 25th power of minus 1 means actually the 25th power of this congruence class minus 1 containing minus 1, and that by the definition of multiplication mod 7 excuse me, it's just this, which is this. So we simply write minus 1. However, minus 1 is congruent to 6 modulo 7. So here the answer is 6. 6 is less than or equal to 6. So that extra requirement is also true here. I mean it has been satisfied. So the first one is 4 and the second one is 6. Thirty-four is similar. Perform each calculation in this time set 15. The final answer should be a non-negative integer no larger than 40. The first one is 5 times 11 minus 3 times 4, and the second one is 2 to the power 82, the 82nd power of 2. This is 55 minus 12, and that is 43, and 43 is 43 is congruent to what modulo 15? If we divide 43 by 15, then we get this 30 plus 13. 13 is a non-negative integer less than 15. So this is equal to 13, and for the second one note that the fourth power of 2 is of course 16, and 16 is congruent to 1 mod 15, so this is equal to 1 in Z15. So 2 to the power 82 is what? If we are thinking of division by 4, then this gives us 80, and extra we have 4. So 2 to the power 4 is congruent to 1, so that means this is equal to 4. 4 is a non-negative integer less than or equal to 14, so this is our answer. Next, complete the proof Theorem 211. Let us recall Theorem 211. Let's recall the statement and then we will prove it. It's about addition modulo n. The various properties of that operation. So the theorem says this, that n is an integer greater than or equal to 2, and we consider any three elements in set n or Cn. Then this is 1 or it is 1. The sum of two such elements again belongs to Cn. This is called closure under addition. Then we have associativity under addition. Not writing the names, you already know. Then the third one is commutativity. Then the fourth one is additive identity. There is this congruence class containing 0, which has no effect on addition. And finally, there is this fifth one, additive inverse. If you add this congruence class to this one containing minus a, then you get the additive identity. And in the text, closure under addition has already been proved and commutativity has been proved. So we now have to prove the others. So we keep these numbers as they are. And we straight away perform the calculation. By the definition of addition modulo n, this sum equals the congruence class containing b plus c. Again applying the definition, we get this. But now inside these square brackets, this is an ordinary sum of integers a, b and c, which we know, the ordinary addition of integers is associative. That is something we already know. So that's why we can write it like this. Again apply the definition of addition modulo n 2 times. And that gives us this. So that's what we wanted to show. Just like ordinary addition of integers, addition modulo n is also an associative operation. Then 4. 4 is also extremely, in fact you can see that all of them are almost trivial. These properties are coming directly from the corresponding properties in the system of integers and its operations, ordinary addition and multiplication. Multiplication, however, it has not appeared yet. It will appear in the next exercise. Anyway, for the sake of completeness, we have to come. For some reason, the ink is not coming properly. Applying the definition of addition modulo n, but this is our ordinary a, so that's just it. Then the fifth one is also similar. That's it. And just like this, there is this next one. I think I need new ink. Just give me a moment, okay? I have to open this bottle. Okay, I hope this works. Okay, so this next exercise, part is 6. Complete the proof of theorem 212. Now theorem 212, you have the statement in the text. It involves the operation multiplication mod n along with addition mod n also. The addition and the multiplication both appear in the distributive law. The others are similar. For example, the product of two such elements is again in set n. Multiplication mod n is an associative operation. It is commutative. Then there is this multiplicative identity, and there is that distributive law. A times b plus c is ab plus ac. I think I have messed up the order, the numbers I have messed up. Maybe this one comes last, but you understand. And that can also be done similarly like this one. It's extremely straightforward, so I will not do it. Okay, so you do it yourself. And now the ink is coming properly, so the previous one isn't working anymore. It's not over. I still have some left in the bottle, but for some reason it's sort of dried up. Maybe I didn't put the cap properly. For each non-zero element, A in C20, decide if there is a non-zero B. Such that their product is 0 in C20. If so, provide such an element B in each case. So this is just a matter of calculations, and it's just this. Note that for any non-zero element B in C20, 1 times B is equal to B, that is not equal to 0. That means for the element 1 in C20 there is no such B that will make this product 0. There is no such non-zero B. So this is one thing. Then two times 10 is 20, and modular 20, that is 0. Okay, and I should write here that for 2 B is 10 and 10 is non-zero, but you can see those things, so I am not going to write them. I will just simply write this and move on. Now we come to 3. So for 3 there is again just like 1 no such b, but we have to show why there is no such b. Here that thing showing that there is no b has been quite easy. For 3 however we have to work a little more. Let there be a b in C20 such that 3 times b is equal to 0. Then b is 1 times b, and 1 it turns out is 3 square. No, what the hell am I saying? It's not 3 square. We are working with modulus 20, no? So it's not 3 square, it's 7. Okay. 1 is equal, let's just first write 1 is equal to 21, because 21 and 1 are congruent to each other, modulo 20. And 21 is 7 times 3 b, but because multiplication mod 20 is associative, so this is 7 times 3b, which is 7 times 0, and that is equal to 0. So if 3b is 0, then b must be equal to 0. We cannot find a non-zero b for which 3b is 0. So for 3 there is no such b. That's what this whole thing means. Then four times 10 also has 2 times 10 in it, so that is equal to, in fact we can take care of the even numbers like this, and we should perhaps write them together so that we don't have to write again and again. Then 4 times 10 is 0, then 6 times 10 is also 0, 8 times 10 is 0, 10 times 10 is of course 0, 12 times 10 is 0, 14, the modulus is 20, no? So we can go like this till 18. We don't care what these products actually are. The fact that each one of them, these first factors, each one of them has a 2 in it, that is enough for these products, all of them to be 0. So for the, if we want to call these elements 2, 4, although these are congruence classes, even if we want to call them even congruence classes, then for each one of them the b that works for us is 10. Other b's may also exist, but we just need one b. Now we come to the odd ones. For the odd ones we have already seen 1 and 3. So what are the others? 5, 7, 9, 11, 13, 15, 17. And for 5 also we, okay, see, just like 2 times 10 is 20, 5 times 4 is also 20. Or instead of writing then here, we can write next. Next, 5 times 4 is 20 and hence it's 0. So we have taken care of 5. There is no non-zero b in set 20 for which 7 times b is equal to 0. That we can directly say because of this calculation. You start from here by, you first assume that there is a b in Z20 for which 7 times b is 0. Then you start from here, and here instead of considering 3b you consider 7b, which according to your assumption is 0. So you get the fact that b has to be 0. So no non-zero b exists for which this is true. Okay. Next, 9. For 9 also the same thing, because you can take care of 9. Okay, I'm saying the same thing, but is it really the same? It is the same thing, but the calculation is a little different from what we have here. Let p belong to C20 for which 9b is equal to 0. Then p is equal to 1b and 1 is equal to 81 because 80 is divisible by 20. So for 9 also no non-zero b exists for which 9b is 0. Then 11. For 11 also the situation is similar. Let p belong to C20 for which 11b is equal to 0. Then one is equal to 121 because 20 divides 120. So for 11 also no such b. Then what about 13? Let such that (13) times p is 0. Then p is equal to 1 times p, and in this case one is congruent to 17 times 13. You do the calculation. Okay, 17 times 13 you calculate, subtract 1 from that, the result of that subtraction will be divisible by 20. So in place of 1 you can write 17 times 13. So for 13 also no such thing, I mean no such b. Next, for 15 however we have one such b, and that b is 4. Four is non-zero and it is in Z20, and this in Z20 this product is 0 because we get a 5 from here. So 5 times 4 is 20, times that extra 3 is there, but we just ignore it. Since we have got 20, so it will ultimately be 0. Okay, so what else? 16 we have already seen, 18 we have already seen, 17 and 19 is there. For 17 this calculation works. Okay, so we directly write for, or we can in fact more directly just write this. There is no non-zero b this is equal to 0. And finally we have 19. Then p is 1 times p, and you please verify that in C20 1 is equal to 19 square. Okay, so these are the things, and this completes the current solution. And related to this, we have the next exercise. For each element, A in C20, decide if there exists a B in C20. This A is article A, okay, and this B is of course our element B, such that the product AB now is 1. If so, provide such an element B. Now here, since we have already gone through the solutions, this new solution, we are going to not write it formally, and instead what we will do, we will just first list all the elements in C20. And then we will say in each case whether such an element exists. For a equal to 0, clearly such a B cannot exist because 1 is not equal to 0. For a equal to 1, B is 1 itself. We express that fact by drawing a loop over 1. For 1 is the B. For 2, we don't have such a B. Do you see why we don't have any B for 2? Because if we had a B for 2, say like this, then what we can do, we can multiply on both sides by 10. Giving us 0 on the left side and 10 on the right side, and that is false because 0 is not equal to 10. And do you see that this is going to happen to all the elements for which previously we found non-zero B's such that the product is 0? That is because you see, any A you take here that has appeared in the previous solution for which you found a non-zero B making the product 0. Now you won't be able to find a B prime such that AB prime is equal to 1, because if you multiply on both sides by 0, after the multiplication the left side will be 0 whereas the right side will be that B. Okay, and B, according to these calculations, in each case where such B, we are able to find such B, that B is non-zero. So 0 is equal to B, that is a contradiction. So for such elements, these new B's cannot be found. And they are all the even congruence classes. So they are automatically ruled out. Among the odd congruence classes also, 5 is ruled out because 5 times 4 is 0. 5 is ruled out, 10 has already been ruled out, 15 is ruled out, any multiple of 5 is ruled out. So these are the only multiples of 5 available. 0 is also there, but we have already ruled it out. Okay, so among the remaining things, the B's are like this. 3 and 7 form a pair. 3 times 7 is 21, mod 20, that is equal to 1. So for 3 the B is 7, for 7 the B is 3. And then 9, for 9 it is 9 itself, again a loop. 9 times 9 is 81, which in C20 is 1. For 11 it is again 11. 11 times 11 is also equal to 1. For 13 forms a pair with 17. 17 times 13 is 1. So for 17 the b is 13, for 13 the b is 17, and 19 forms the loop. 19 times 19 is 1 in C20. So these are the elements for which such b's can be found: 1, 3, 7, 11, 17, 19. Okay, and for the rest we don't have such b's. But I urge you to write this solution properly. Okay, like how a solution has to be written, you do that along with the justifications for these things. Why, for example, 5 has been ruled out, why 4 has been ruled out, those things have to be written. Next, 39. Show that if P is prime, then there are at most 2 elements. In set P such that at most 2 elements A. Okay, that is understood, such that A square is equal to 1 in this. Find an example of a composite P where there are more than 2 solutions. Okay, let A be in CP such that A square is equal to 1. We could have mentioned the, okay, let us do that now. Let A be equal to the congruence class P where P is an ordinary integer. Then this equation translates into this this 1 actually means this, and hence into this congruence, or in fact we can go one step further and write that p divides b square minus 1. Thus, now b square minus 1 is of course b plus 1 times b minus 1, and p being a prime would then divide either b minus 1 or b plus 1 or both. And then from there we can go forward. Or p divides b plus 1. Thus, this congruence class is equal to 0, or this is equal to 0. These imply that if you apply the operations modulo p, I mean the operations available in this system Cp, then from this condition you get A equal to congruence class P equal to 1, which is equal to 1. Or if you use this one, then you get A equal to this equal to minus 1, which is minus 1. Minus 1 in ZP has to be interpreted as P minus 1. The fact is that A can either be 1 or minus 1. So there are two possibilities. So the equation, because we are writing it as an equation and we have already considered A to be an element in ZP, so we use X here. Has at most two solutions in CP, and those two solutions are 1 and minus 1. Why are we writing at most and not exactly two solutions? Do you see that? That is because there is a case in which 1 can be equal to minus 1. It's in Z2. Okay, in Z2 1 is equal to minus 1. Now this type of equations, when one looks at them, it can create confusions, and those confusions, if you are not sure of what you are dealing with, then this type of confusions can destroy everything you know. Okay, from this you will conclude that 2 is equal to 0, and from that everything will fall apart. However, you must keep in mind that this 1 is not the ordinary integer 1. It is the congruence class 1, and this is the congruence class minus 1, and they are equal as sets, and that is because 1 is congruent to minus 1 modulo 2. there is a meaning to this equality. It's not ordinary equality. It's equality between two. I mean, it is equality, but in this set, it's an equality relation. So we write at most two solutions. Now you can see that here primality of P has played a role. Only because P is a prime have we been able to write that either this happens or this happens. This clearly is not the case when P is not a prime. For example, if P is 6, I'm just talking about this too, okay. 6 is not a prime, and 6 divides 2 times 3, but 6 neither divides 2 nor divides 3. Okay, so for a composite integer, this property is not there necessarily. Now we have to find a composite P for which in the corresponding modular system ZP, there are more than two solutions to this equation, and one such number is this. Note that in Z12 we have two solutions. Of course, we can say from these calculations itself, 1 square is always equal to 1, and minus 1 square, minus 1 in this context is the congruence class containing minus 1, which also contains 11, so 11 square is 1. But there is something else also whose square is 1. 7 square is 49, and 49 is congruent to 1 mod 12. So 7 square is also equal to 1. And in Z12 we are writing no, so that means this 1, 11, 7, these are congruence classes coming from Z12. That is, the modulus is 12. This next one is interesting. Let A and B be integers. Show that if A is congruent to B modulo P for every prime P, then A is equal to B. Solution: suppose A is not equal to B. So we will try to generate a contradicting situation. So that means either A is greater than B or B is greater than A. We assume without loss of generality that A is greater than B. Okay. Since there are infinitely many primes, so we are using this result of infinitude of the set of primes here. We can choose a prime P greater than A minus B. We are not saying whether A or B or both are positive or negative. They can be anything, but because A has been chosen to be greater than B, so A minus B is a positive integer. But no matter how large A minus B is, we can always find a prime number greater than A minus B, because otherwise the set of primes would be finite, which is not true. But then P does not divide A minus B. Why? Because A minus B now is a positive integer less than B. So that is why P does not divide A minus B. This contradicts the hypothesis that A is congruent to B mod P. It's given that this is true for any P, but for this particular P we see that this is not true, this is being violated. So that is why we have arrived at a contradiction. So our supposition is wrong. And we must have A equal to B. Find an integer A such that A is congruent to 2 modulo 3, A is congruent to 4 modulo 7, and A is congruent to 3 mod 10. Simultaneously. So that means here we have to use Chinese remainder theorem. Now going through that proof of the theorem, we will just follow what we did there in the proof. I mean whatever we have in the proof systematically, and we are going to use the notations we see in the proof. So we directly write here D1 is the product of all the moduli divided by this first modulus. So that means it's the product of 7 and 10. So this is 70. Just like that, D2 is the product of 3 and 10, 30, and D3 is the product of 7 and 10, 70. Now, have I made a mistake? This is 70. Oh, so this is 21. It's the product of 3 and 7. Okay. Now, let u1 and nu1 be integers such that 3u1 plus 70 nu1 equal to 1. Okay, and this 3 is this modulus, first modulus, that is not in this product. We now have to find u1 and nu1, actually nu1, but in the process u1 will also be simultaneously found. And I am not writing the details. You will see that. So here I write find u1 and nu1 yourself. It turns out that u1 is minus 23 and nu1 is 1. If you cannot figure out how to find u1 and nu1, you just keep in mind that the greatest common divisor of 3 and 70 is 1. So you follow the Euclidean algorithm for finding the GCD of two given integers. Like you first divide 70 by 3, you get some remainder. You then divide 3 by that remainder, and you keep doing this until you get 1, and then you have to use the calculations in the reverse order to express 1 as a linear combination of 3 and 70 with these coefficients u1 and nu1. After that, after you find that expression, you will see that u1 becomes minus 23 and nu1 is 1. Similarly, if u2, u3, or because we are taking u2 and nu2 together, so let's just write them like that, and u3 and nu3 all are integers such that u2 plus 30 nu2 is equal to 1 and 10u3 plus 21u3 is equal to 1, then seven u2 plus 13u2 equal to 1, then u2 is 13, nu2 is minus 3. Here also you have to do that calculation. You calculate the GCD of 7 and 30 using the Euclidean algorithm. Divide 30 by 7 and then do what you are supposed to do according to that algorithm, and then use the calculations in the reverse order. Express one as a linear combination like this. From that you can find that u2 is 13, u2 is 3, and just like that u3 turns out to be minus 2 and nu3 is 1. So the integer that we are seeking, let us call that b, although we have been asked to find a, but let's just call this b. This is d1 nu1 a1 plus d2 nu2 a2 plus d3 nu3 a3, and according to the notation we see in the statement of the Chinese remainder theorem, a1 is this one, a2 is 4 and a3 is 3. So putting everything in this expression, we see that it becomes minus 157, and that is congruent to 53 mod 210, and this 210 you can see is the product of the moduli 3, 7 and 10. So 53 is our A. One can verify that 53 is congruent to 2 mod 3, then (53) is congruent to 4 modulo 7, and 53 is congruent to 3 mod 10. It's not necessary that you have to apply the Chinese remainder theorem, but that's the way to go. Okay, instead of blindly looking for an integer a, you can use the Chinese remainder theorem, and that's because these moduli 3, 7, 10, these are relatively mutually relatively prime or mutually co-prime. The GCD of any two of them is 1, so we are able to use the Chinese remainder theorem. And lastly, let us see that we actually have these congruences. 53 minus 2 is 51, which is divisible by 3, because 5 plus 1 is 6, which is divisible by 3. 53 minus 4 is what? 49, that is divisible by 7, and 53 minus 3 is 50, which is divisible by 10. So yes, 53 is an answer. And the next one is also similar, which I will not do. I leave this solution to you. Find integer a such that a is congruent to 3 modulo 8, also a is congruent to 4 modulo 11, and a is congruent to 7 mod 15. Simultaneously. So this one you please do as a homework. So in this section we had these exercises. In the next video we will start a new section, or I think we have completed one chapter itself. I am not sure. We will see. And tomorrow we of course have tau's analysis. So that will be all for tonight. If you want to say something, you can write in the comment section below, or you can mail me at my usual address. So that being said, see you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.